It's a fundamental theorem of calculus. And again, BC students have seen this stuff before, so we'll kind of zip through it sort of quickly here. It has two parts to it. And we'll start out with part two. And that's actually how you are going to evaluate an integral when you have a definite integral, lower and upper limits. And simply take the antiderivative at the upper limit and subtract away the value of the antiderivative evaluated at the lower limit. So that's why we finished up chapter 3, learning about antiderivatives and focusing on that when we got into chapter 4. So looks like in this one we are going to find the antiderivative, and the antiderivative of 6x is going to be 3x squared. Antiderivative of 14x. And we're very tempted to say plus c, and that's fine, but we'll see where we don't really need to do that. We'll evaluate this at the upper limit of 5, and then we'll subtract away what we get when we evaluate at 2. So when we put a 5 into here, I would think we would get 75 minus 70 plus c. So I think we would get 5 plus c. Then we're going to subtract away what we get when we put a 2 in here. When we put a 2 in here, we're going to get 12. 12 minus 28 is negative 16. And we're going to have that plus c still. Well, I think we can see pretty quickly with a definite integral, you don't have to spend any time on your plus c. 100% of the time, you're going to end up with the c minus c, and it's gone. So the value of this integral is going to be 21. This one, antiderivative of 3x squared is x cubed minus antiderivative of 6, 6x. So I'm going to ignore the plus c, realizing that it's going to go away, realizing that I'm working with a definite integral. I'll evaluate this between 1 and 3. And putting a 3 in, we get 27 minus 18. And then we'll subtract away what we get when we put a 1 in. And we have 1 minus 6. So we're going to get a 14. So that's fundamental theorem of calculus part 2. All right, now, part 1. Part 1 relates the derivative and the antiderivative. If g is equal to the integral of f, if g is the antiderivative of f, then the derivative of g is f, relating the antiderivative and the derivative. Now, let's do this two different ways. Let's do this the long way and the short way. Long way is what we just did. Remember, we're looking for g prime of x, and g of x is equal to this integral here. So we're going to evaluate the integral. We are going to find the antiderivative, which we found in the previous example was x cubed minus 6x. We'll evaluate this between 2 and x, and we're realizing that this is g of x. So let's make that real clear. So the first thing we do is we evaluated x. Oh, and I'm sorry, we should have called this since the variable was t. I really should have called these t's. So, t cubed minus 6t. Now I replace the t's with x, and evaluating at my upper limit, I get x cubed minus 6x's. And we'll subtract away from that the antiderivative evaluated at 2. 8 minus 12 is negative 4. So g of x is equal to x cubed minus 6x plus 4. Now the goal is to find g prime of x, so we'll take the derivative of that. Derivative of that is 3x squared minus 6. And you may notice that that's the same as this thing, just dropping the x in place of the variable. And is that always going to work? And the answer to that is yeah, sort of. Yeah, that's always going to work. You're going to take the antiderivative, then take the derivative of it. Those counteract each other. And so you're left with what you started with. Question comes up then, does this number down here even matter? And the answer to that is no, it really doesn't matter. When I put a 2, when I put any constant into the antiderivative, I am going to get a constant. And when I get a constant and then I'm going to take the derivative of it, constant's going to go away. So the lower limit, the number that we have as part of this integral, is insignificant because its derivative is going to be 0. So, shortcut is take this variable, which better be in the upper limit, we'll see why in a little bit, and just drop it in place of that variable. So we go to our next example. I better make sure there weren't any more. That was it. We go to the next one, and I'm tempted to just drop this guy in here and say, well, this is going to be 4x squared minus 2. Well, we're going to do this 2 ways, but I'm kind of guessing that that's what it's going to be. Let's do this a long way, and let's find the antiderivative of this guy. G of x is equal to, and that would be 2t squared minus 2t evaluated between 0 and x squared. So g of x is equal to, when I drop this guy in, I'm going to get 2x to the 4th, x squared squared, minus 2x squared. And then I'm going to subtract away from that what I get when I put a 0 in here, which is 0. So there's g of x. When I find g prime of x, I get 8x to the 3rd minus 4x. And that is not what I had predicted the answer would be. And so what we'll find here is, since we are finding a derivative, we have to use what we can think of as the chain rule. Sure, go ahead and drop this guy in there. And call this 4x squared minus 2. But what we'll have to remember is we have to multiply by the derivative of this thing. When I multiply my, we'll drop that into integrand. When we multiply that by the derivative, 2x, we do indeed get the correct answer of 8x cubed minus 4x. So it's not as simple as just dropping this in place of the variable. We got to remember to drop it in and then multiply by the derivative. that thing that we dropped in. We can consider that the inner function. And had we done that back here, just dropped this in and called it 3x squared minus 6, and then multiplied that result by the derivative of what we dropped in, well, we're going to get the same thing. Down here, we want the derivative of g of x. Well, I'm thinking we're going to drop this guy in. We're going to get, I'm not going to do this the following way. I think we're pretty confident with what we're doing here. We're going to get secant squared of x to the fourth times the derivative of this guy, which would be 4x to the third. And since I prefer the coefficients to be brought up front, I'm going to call it 4x to the third, secant squared of x to the fourth. Down here, I'm dropping this in place of the variable. I'm not doing this a long way. I'm going to call this f of psi of x. And let's multiply that by the derivative of what we dropped in there, cosine of x. Whatever that is. Okay, final slide. Properties of definite integral. If mistakenly or unpurposely, somebody puts the smaller number on top and the bigger number on the bottom, that's a problem. We talked about this as properties of integrals in section 4.2. What we need to do is we need to flip-flop those guys. You need to change position. You need the smaller number on the bottom, bigger number on top. But when you do that, you have to take the opposite of that integral. So that was property we talked about. So here, I would say that g of x, since the small number is the upper limit, bigger number is lower, g of x is actually going to be equal to the opposite of this. We're going to go from 1 to 3, and we're going to have 3x squared minus 6. Now, if we were actually to figure out what g of x is, we don't ask for the derivative in this case, that's fine. Let's see, we would have the opposite. We'd have x cubed minus 6x. Evaluated between 1 and 3. And when we put a 3 in here, I think we did this before, and we got 9. Minus, when we put a 1 in here, I think we got negative 5. We're going to remember that in the end, we're going to take the opposite of this answer. So I think we're going to get negative 14 as our final result. Now, what if such a problem does involve finding the derivative? Okay, first of all, g of x, we would have to, and when we're going to find the derivative, we're going to consider x to be the equivalent. We do want to switch this around. We're going to be taking the opposite of 2x. 5x plus 30. Now, we could jump down here and find the derivative right now. We can just drop this guy in there. Well, I should put my, first of all, I should pay some attention to what variables we're using. That's a t, isn't it? And I do have a dt here, and I shouldn't be in such a hurry. All right, I'm going to drop my x in place here. And I'm going to get 5x plus 13. Since it's a plain old x, whether I worry about or I even forget about multiplying by its derivative, I'm going to get the same answer. I'm just going to take the opposite of it. But if I had to solve for g of x, I think what I would have is, let's see, it's going to be the opposite. I'm going to take the antiderivative of this. 5t squared over 2 plus 13t. I'm going to evaluate that between 2 and x. And so we're going to have the opposite of 5x squared over 2 plus 13x minus whatever I get when I put a 2 in here. If I put a 2 in here, I think I get 20 over 2, so I got 10. 10 plus 26 is 36. So that is what g of x is. And if we then take the derivative, I think we would see x plus 13. Again, the lower limit, which is a constant, results in a constant, the derivative of which does not exist. Or it's a zero, I guess I should say. Zero exists. All right, there's your fundamental theorem of calculus.